There is an experiment chemists do in their first year at university. They take a bright orange solution, almost like orange juice, and add a few drops of alkali. The orange instantly turns yellow. Then they add acid. The yellow returns to orange. Add a reducing agent, and the solution suddenly turns green. Deep, rich, almost emerald. Another reagent, and now it's purple, blue, green again. The students look at this and think something's definitely wrong here. How can the same solution be orange, yellow, green, and purple all at once, depending on what's added to it? It looks like a trick, like a chemical illusion. But it's not an illusion. It's one element, 24 protons in its nucleus, atomic number 24, chromium. And that's what makes it truly strange. The same element that's putting on this show in the lab flask is, right now, in your blood. In a negligible amount, less than 1 million grams per liter. But without it, your insulin would work worse. And this same element underpins all modern surgery, all aviation, all microelectronics or sonics. Its atoms store within themselves a record of exactly when oxygen appeared on Earth. That is, when life as we know it became possible. One element, an infinite number of faces. But we won't start with a laboratory. We'll start with a piece of red stone that traveled from Ural mines to Parisian offices and ultimately changed the we understand color. Red stone from the Urals, 176. Yekaterinburg. Mines near the Berezovka River. Miners bring something unusual to the surface. A heavy mineral, dense, orange-red with a metallic sheen. Such things had never been seen in the Urals. Samples are sent to Johann Gottlob Lehmann, a German naturalist in Russian service. He describes the mineral, gives it the working title Red Lead Spar, and publishes a short paper. A year later, Lehmann dies. The circumstances are murky. Arsenic poisoning during another chemical experiment is suspected. Or perhaps it was simply an accident. The 15th century wasn't inclined toward detailed investigations. But the mineral remains. Samples are sent to Europe, to the collections of naturalists, to the Mithridum Museum, and to the private offices of scientists. A beautiful exotic from the distant Urals. It will be called crocoid, from the Greek krokos, saffron, because its color is warm, spicy, almost edible. For 30 years, croquet lies in collections, uninterested. And then, in 1797, Paris, Louis-Nicolas Vauquelin takes up the croquet. He is 35 years old. He was a student of Antoine Lavoisier, the same one executed 3 years earlier during the Terror. They say Lavoisier made a deal with the executioner. After his head is cut off, he will blink as long as possible to check for consciousness. The judge at his trial famously remarked, "The Republic has no need of scientists." The legend may be exaggerated, but the fact of the execution is not. Vauquelin is working in a different time. The terror is over. Science is once again in vogue. He takes a sample of crocoid, dissolves it in hydrochloric acid, and carries out a series of reactions methodically, precisely, without haste. And suddenly, he obtains something no one has seen before. A new metal, gray, hard, shiny. He calls it chromium, from the Greek chromium. Color. Why color? Not because the metal itself is bright. In its pure form, it is gray and, frankly, unsightly. But because its compound is a veritable rainbow. This is precisely what happened in Vauquelin's flasks while working with crocoit. Each new compound yielded a new hue: orange, yellow, green, violet, red. This is the only element in the periodic table whose name literally means paint. Concurrently with Vauquelin, the German chemist Martin Heinrich Klaproth independently analyzed the same crocodile and also came to the conclusion that it was a new element. Vauquelin published his results first. Klaproth, without scandal or offense, is his priority. It happens in science. Why does chromium change color? And why is this important? Now comes the most interesting part. Why can chromium do what it does? Why does the same element produce different colors? This is not a coincidence. It's quantum mechanics, but one that can be explained without formulas. A chromium atom has 24 electrons. They occupy orbitals. You can imagine this like the floors of a house, only a very small and very strange house, where the rules of occupation don't match anything in everyday life. Most elements occupy their orbitals sequentially in a strict order. Chromium doesn't. It does something unexpected. It redistributes its electrons so that the 5 inner orbitals are occupied by exactly 1 electron each. This is called a half-filled-in electron shell. It is exceptionally stable. Nature favors symmetry, and it is this architecture that gives chromium its multicolored appearance. When a chromium ion enters a chemical compound, its inner electrons find themselves in the electric field of neighboring atoms. This field splits the electrons' energy levels. They are no longer equal and are separated into higher and lower ones. The difference in energy between the levels corresponds to the energy of a photon of a certain wavelength. It is this wavelength that the electrons absorb, and everything else is reflected. Which wavelength is absorbed depends on how strong the field is created by neighboring atoms. And this, in turn, depends on which atoms are nearby and at what distance. Hence the main paradox of chromium. Ruby is red, emerald is green. They are opposite ends of the visible spectrum, more than 150 nanometers of difference in wavelength. But both stones contain the same chromium ions in the same state. One element, one state. In ruby, the chromium ion is embedded in the crystal lattice of corundum, an aluminum oxide mineral. The distance from the chromium ion to the surrounding oxygen ions is slightly less than 2 angstroms. This distance creates an electric field of a certain strength. The field splits the energy levels of the electrons so that the energy difference corresponds to green light. Green is absorbed. Red is reflected. In emerald, chromium is embedded in a lattice of beryl, another mineral. The distance to neighboring atoms is slightly greater. The field is slightly weaker. The splitting is different. Now red light is absorbed. Green is reflected. The difference in distance between the atoms is less than 1 angstrom. That's approximately 1 billionth of a meter. This tiny difference changes the color from red to green. One atom. 2 of the most famous gemstones in human history. 2 polar colors. This isn't mysticism, it's physics at the level of distances that are unimaginable. So where did chromium come from on Earth? On our channel, we've already talked about how elements are born in stars, nuclear fusion, supernova explosions, and the dispersal of matter across the galaxy. We cover this in almost every episode, so here's a quick overview. Chromium atoms were fused in the cores of massive stars that exploded before the birth of the solar system. Some of this material became part of the protoplanetary cloud and eventually ended up here, beneath our feet. Let's move on. Earth contains a lot of chromium. It's about the 21st most abundant element in the Earth's crust, with about 100 milligrams per kilogram of rock. But it's distributed unevenly. Chromium is primarily found in ultramafic rocks of the mantle, ferrites, and dunites. When tectonic plates collide, these rocks are sometimes forced to the surface. This is where the main chromium mineral chromite forms. It's a compound of iron, chromium, and oxygen in a single crystal. The largest chromite deposits are in Kazakhstan, South Africa, India, Zimbabwe, and Finland. South Africa, according to various estimates, holds more than 70% of the world's proven reserves. But more on that later. Now let's talk about what chromium has done to painting, and why what we see in museums isn't quite what artists painted. A traitor in colorful words. At the beginning of the 10th century, paint production was undergoing a revolution. New synthetic pigments were brighter, cheaper, and more accessible than traditional ones. Among them was chrome yellow, a compound of lead and chromium. A rich, garish, almost aggressive yellow. Artists rushed to use it. Among them are Vincent van Gogh, Sunflowers, The Varley Bedroom, and Wheatfield with Crows. All of Van Gogh's famous yellows are chrome yellow. Van Gogh specifically chose this pigment for its intensity. He wanted the yellow to scream from the canvas. This is exactly how he saw the southern sun of Provence. But chrome yellow turned out to be a traitor. The chromium in this pigment exists in a special state that is unstable when exposed to ultraviolet light. Under its influence, the chrome slowly but inexorably changes state, transforming into another form. And with it, the color, the bright yellow gradually darkens, turns brown, and becomes a dirty brown. If you want to understand exactly what happens at the molecular level, remember our discussion about the splitting of energy levels. When chromium changes state, the type of light it absorbs also changes. This changes the color. This process takes decades. More than 130 years have passed since Van Gogh's death. In 1890, all this time, the chrome yellow has been slowly changing color. In 2011, a research team from the University of Antwerp, together with the European Synchrotron Radiation Facility in Greenbelt, conducted a detailed study of the paint layers of Van Gogh's paintings. Scientists used methods to determine the chemical state of pigments without physically touching the canvas, without destroying the painting. The results confirmed their suspicions. The darkening of yellow tones is a direct consequence of changes in the state of chromium in the pigment. Moreover, the process occurs unevenly across the entire surface, but locally, where the pigment is closer to the surface and receives more light. This means that what we see in museums today, the sunflowers, in London's National Gallery, the bedroom, in the Musée d'Orsay, are not what the artist himself saw. They are versions of his paintings, altered by the chemistry of a single element. This discovery launched a new direction in restoration science, predictive chemical modeling. Now restorers analyze the chemical composition of pigments even before degradation becomes visible to the naked eye, and develop storage conditions that slow the reaction. Darkness, low temperature, controlled humidity, all this slows the degradation of the pigment. Chrome continues to repaint the painting, slowly, imperceptibly, but it is true. An accident that changed medicine. 1913, Sheffield, England. A research laboratory at a metallurgical plant. Metallurgist Harry Brearley is tasked with finding a steel that wears less from the heat of intense rifle fire. Ooh. The task is concrete, practical, and unadorned. Brearley works methodically, casting steel samples with different compositions, testing them and discarding them. Some of the samples are simply stored in a corner of the lab. They are unsuitable for his task, and he forgets about them. Several months pass. One day he notices that most of the samples he set aside are covered in rust, but not all. A few, those with a chromium content above 10.5%, look like new, not a single spot of corrosion. Brearley begins analyzing, checking again and again. The result is reproducible. High chromium steel does not rust. The mechanism of this phenomenon was understood later. At chromium content of 10.5% or higher, a very thin film of chromium oxide spontaneously forms on the surface of the steel. Its thickness ranges from 2 to 3 nanometers. This is approximately 30,000 times thinner than a human hair. The film is transparent, so the steel looks like regular steel, not the green-painted surface. It is also self-healing. If scratched in the presence of atmospheric oxygen, it will repair itself within seconds. This is why stainless steel does not rust. Not because it is special in itself, but because chromium constantly builds an invisible protective shield on its surface. At the same time, in Germany, metallurgists from the Grupo company patented another type of stainless steel with high nickel and chromium content in 1912. The priority dispute between the British and German schools dragged on for years. Both camps had grounds for claiming primacy. But the outcome is more important. The world received a material without which modern civilization would be impossible. Think about that for a second. Surgical instruments before. Stainless steel, they rusted even after sterilization. Kitchenware. Reactors in chemical plants. Food industry pipelines. Turbines in power plants and aircraft engines. The hulls of sea vessels. Medical implants, hip joints. Dental crowns, stents in coronary arteries, pacemaker housings.
All this is based on a discovery rarely made by chance, looking at a pile of rejected samples in the corner of the lab. Today, about 85% of the world's mined chromite goes into the production of stainless steel and chromium-containing alloys. Global chromite production is approximately 40 million tons per year. This is not just an industrial statistic. Wars, diplomatic intrigues, and major geopolitics lie behind this figure. There are facts that seem like an exaggeration until you begin to delve into the details. Here is one of them. The outcome of World War II was partially determined by access to chromite. It's not oil that everyone's talking about. Neither are tungsten or molybdenum, which are mentioned less frequently. Chromite is almost never mentioned. The chain is simple. High-quality armor steel requires chromium. Without it, it doesn't achieve the necessary hardness and toughness simultaneously. Armor steel is what makes tanks, self-propelled guns, armored personnel carriers, and ship hulls. Without high-quality armor steel, warfare as it was waged from 1939 to 1945 was technologically impossible. Germany had no significant chromite deposits of its own. The country was entirely dependent on imports. The two main sources were Turkey and southern Rhodesia, today's Zimbabwe. In this situation, Turkey acted like a classic neutral seeking to profit from all sides at once. It sold chromite to the Germans and simultaneously received diplomatic pressure from the Allies demanding a halt to these supplies. This maneuvering continued for several years. British intelligence and American diplomats worked systematically on this problem. They understood that cutting off chromite supplies to Germany would seriously hamper the German military industry. According to Allied analysts, Germany's chromite reserves were sufficient for several months of normal armor steel production. This meant that within a few months of the cessation of supplies, the quality of German armor would begin to decline. In 1944, after intense diplomatic pressure and given the obvious change in the military situation, Turkey stopped chromite supplies to Germany. There is no direct connection with Germany's capitulation. It was too late. But the very fact that the Allies had spent years deliberately fighting for control of Turkish chromite as a military priority speaks volumes. The Soviet Union took a fundamentally different position in this regard. Large chromite deposits in the Urals near the Saranovskoye deposit in the Perm region and in Kazakhstan gave the country strategic self-sufficiency in this element. The armor of Soviet T-34 tanks was made of alloyed armor steel containing chromium and manganese. This wasn't just metallurgy. It was the geology of the Urals working for victory. After 1945, the importance of chromium didn't decline, it actually increased. During the Cold War, a situation arose that American strategists called the chromium problem. The world's largest reserves of chromite, more than 70% of the world's proven reserves, according to some estimates, are concentrated in South Africa, in the Bushwell Igneous Complex. This geological structure formed approximately 2 billion years ago when a massive amount of magma intruded into the Earth's crust and solidified in layers. These layers contain platinum, chromium, and vanadium in industrial concentrations. The Bushwell Igneous Complex is one of the richest ore regions on the planet. The problem: in the 1970s, South Africa was an apartheid state. Western countries officially condemned this regime, imposed sanctions, demanded change, and simultaneously continued to purchase South African chromium because their military industries could not function properly without it. When the Soviet Union began to actively operate in Africa, supporting leftist movements in Angola, Mozambique, and Zimbabwe, American analysts began to explore the possibility of Moscow taking control of the South African and Zimbabwean chrysosomite deposits. This scenario was featured in analytical papers titled The Chromite Threat. The answer was unpleasant. The Western military and aerospace industries would find themselves in a critical state of dependency. This is not a conspiracy theory. It is a documented part of Cold War-era strategic planning. One chemical element is at the center of a global game. Today, the largest producers of ferrochrome are South Africa, Kazakhstan, India, and China. China is the largest consumer, but not the largest producer of the raw material. It imports most of its chromite and is actively investing in mining projects in Africa. History, as you can, repeats itself. Now for the dark side, the one manufacturers have preferred to keep quiet about for decades. Chromium exists in several states, and this is fundamental to its biological action. Trivalent chromium is found in unnatural minerals, is a component of soil, and is essential for the body. It is poorly soluble in water and poorly penetrates cell membranes. It is relatively harmless. Hexavalent chromium is a completely different substance from a biological perspective. The International Agency for Research on Cancer, IARC, classifies its compound as a Group 1 human carcinogen. This is the highest category of evidence. Lung cancer, nasal mucosa and paranasal sinus cancer, stomach cancer. The effects of chronic occupational exposure have been documented. The mechanism of cellular penetration is one of the most insidious in toxicology. Hexavalent chromium in the form of particles dissolved in water is almost identical in shape and electrical charge to the sulfate ion, one of the most common in biology. Cellular transport proteins designed to transport sulfate fail to recognize the substitution and readily smuggle chromium into the cell. This is molecular mimicry, biochemical Trojan horse. Once inside, hexavalent chromium begins to convert to trivalent chromium. This conversion produces highly reactive intermediates and reactive oxygens, species hydroxyl radicals, and peroxides. These particles attack DNA, cause strand breaks, form cross-links between DNA and proteins, and lead to chromosomal abnormalities. The result is mutations. With sufficient dose and exposure, cancer can develop. Workers in galvanic shops, chrome plating plants, and chrome pigment factories paid for this with their health often, unknowingly, often for decades. There's a story that most people know from a Hollywood movie, but the movie is a simplification. The real story is more complex, more terrifying, and more chemically accurate. Hinckley is a small town in the Mojave Desert, California. A few hundred houses, dusty roads, and heat most of the year. Since 1952, a Pacific Gas and Electric compressor station has been operating here, a hub for a pipeline transporting natural gas to Southern California, Iriutonio. This station used a chromium compound in its hexavalent form as an anti-corrosion additive in its cooling water. This was standard practice at the time. Hexavalent chromium prevents rusting of metal parts in the cooling system. The same passivating film we've already discussed. The waste cooling water, which contains high levels of chromium, is discharged into open earthen settling ponds. The calculation is simple. The water evaporates and the residue settles. No one thinks about the chromium filtering through the soil into the aquifer. Hinckley residents draw water from wells, drink it, water their gardens, and bathe their children with it. From 1952 to 1966, 14 years. Then Pacific Gas and Electric changed its cooling technology and stopped using chromium. The ponds were filled in and forgotten. But in the aquifer beneath Hinckley, hexavalent chromium didn't disappear. It continued to migrate with groundwater, spreading over an ever-increasing area. Residents continued drinking well water. In the late 1980s and early 1990s, Hinckley residents began to notice a disproportionately high rate of cancer in the town, with tumors in rare locations and children with unexplained illnesses. But no one connected it to the water because no one had tested the water for chromium. In 1991, paralegal Erin Brockovich, an employee of a small law firm, accidentally discovered medical records in a Hinckley property purchase. Why would a company submit medical records in a real estate case? It was odd. Brockovich began asking questions. She traveled to Hinckley, talked to residents, collected medical records, took water samples, and created a disease map. The picture is clear. Cancer rates in Hinckley are several times higher than normal, and water contamination with hexavalent chromium is a documented fact. In 1993, a class action lawsuit was filed on behalf of more than 600 Hinckley residents. The company denied liability In 1996, an out-of-court settlement was reached. The sum was $333 million. At the time, it was the largest environmental lawsuit payout in U.S. history. In 2000, Steven Soderbergh directed the film Erin Brockovich. Julia Roberts won an Oscar for Best Actress for her role. But behind the Hollywood ending are real people with real illnesses, and the fate of Hinckley after 1996 is not as rosy as in the movies. Hexavalent chromium contamination in the groundwater turned out to be more extensive than expected. Cleanup continued for years. As of 2010, contaminated groundwater beneath Hinckley continued to expand despite remediation efforts. Hinckley's story is no exception. In Bangladesh, in the Hazarabad district of Dhaka, liquor factories have been discharging chromium-containing water sources into the Burganga River for decades. In 2012, the international organization Pure Earth included this area in its list of the 30 most polluted places on Earth. Similar stories are told in India, China, and Eastern Europe. Different geographies, the same chemistry. The European Union banned the use of hexavalent chromium compounds in electronics with a special directive in 2003. Many countries have introduced strict standards for hexavalent chromium in drinking water, but already contaminated areas require decades also to remediate, and now comes don't expect that most don't expect. The same element that poisoned Hinckley's groundwater in its hexavalent form is currently in your bloodstream in its trivalent form. And without it, your body would function worse. 1957, National Institutes of Health, Bethesda, Maryland. Biochemists Klaus Schwartz and Walter Mertz are experimenting on rats. They feed the animals a completely synthetic, chemically pure diet with controlled levels of all known nutrients and discover that the rats develop a carbohydrate metabolism disorder. The animals poorly absorb glucose even with normal blood insulin levels. Something is missing from the synthetic diet. Schwartz and Mertz begin methodically adding micronutrients to the diet, one by one. Vanadium has no effect. Molybdenum has no effect. Nickel has no effect. And trivalent chromium. The glucose absorption disorder disappears. This is how the so-called glucose tolerance factor was discovered. Trivalent chromium found in certain biological complexes enhances the binding of insulin to receptors on the cell surface. Without sufficient chromium, cells are less sensitive to insulin. They need higher concentrations for the same effect. The daily requirement for chromium for an adult is 25 to 35 micrograms. This is literally nothing compared to other elements. The daily requirement for iron is 10 to 20 milligrams, several hundred times more. But this doesn't mean chromium can be neglected. Where is chromium found in food? Whole grain cereals and bread, broccoli, grape juice, beef liver, seafood, especially oysters, and brewer's yeast. Heat treatment does not destroy chromium. Unlike many vitamins, it is thermally stable, but refined foods contain significantly less of it. About 80% of chromium is lost during the processing of grain into white flour. This is an important detail for our audience. With age, the absorption of chromium from food decreases. This is due to changes in the acidity of gastric juice and the functioning of intestinal transport systems. However, the need for it remains. This is one factor, not the only one, but a well-documented one, that researchers associate with increased insulin resistance in middle-aged and older adults. The question of chromium supplements, chromium picolinate and chromium nicotinate, are actively discussed in the scientific literature. Meta-analyses show a moderate positive effect in people with already impaired glucose tolerance. In healthy people with a balanced diet, the effect is minimal. This is not a miracle cure for diabetes. It is a micronutrient without which the biochemistry of insulin signaling works slightly less effectively. There is a paradox that should be stated. Frankly, chromium is one of the most important materials in modern electronics, but almost no one working with computers knows this. Here's how it works. When manufacturing microchips and printed circuit boards, engineers need to deposit metal conductive traces onto the surface of glass, silicon, or a polymer substrate. Copper is a logical choice for a conductor. It is inexpensive, conducts electricity well, and is easy to process. The problem is, copper doesn't stick to glass and silicon. Place a copper film on a glass plate and it will peel off. Solution. First, apply a layer of chromium, extremely thin, from a few nanometers to several tens of nanometers. Chromium adheres extremely well to silicon oxide, and copper. It acts as an adhesive sublayer, a chemical bridge between two materials that would otherwise resist interaction. Your smartphone, laptop, tablet, each of them contains layers of chromium you'll never see. They're hidden within the multi-layer structure of microcircuits beneath copper traces beneath dielectric layers. A few grams in total, but functionally critical. There's another application, too. Photolithographic masks are templates through which ultraviolet light prints a pattern of transistors on a silicon wafer. The mask is a quartz plate with an opaque pattern applied to it. The material for this pattern is chromium, because chromium films absorb ultraviolet light well in the required wavelength range and are exceptionally stable. They do not degrade under the intense ultraviolet radiation of the manufacturing process. Every processor produced over the past half-century, from the first integrated circuits to modern chips a few nanometers thick, has passed through a chromium photomask at some point in production. Chromium is present in the DNA of modern microelectronics. Invisible, but indelible. But the most beautiful story of chromium in physics is not electronics. It is the moment when chromium first emitted light. Hughes Research Laboratories, Malibu, California. The morning of May 16, 1960, across 2010, physicist Theodore Maimon, 32, a Stanford PhD candidate, had been working for months on a setup that most of his colleagues considered a dead end. Lazar's idea, light amplification by stimulated emission, of radiation had been theoretically developed back in the 1950s. Charles Townes at Columbia University created the maser, an analog for the microwave range. Townes would later share the 1964 Nobel Prize with Soviet physicists Prokhorov and Basov for this very reason. But no one had been able to create a visible light laser. Many believed that ruby was a poor active medium, with too many losses and too low an efficiency. Maimon's research grant for this project was rejected. He continued working on his own enthusiasm and the laboratory's resources. At the center of his setup is a cylindrical synthetic ruby, about 2 centimeters long and about 1 centimeter in diameter. The ends are polished and silver-plated, and one is completely reflective, the other translucent, transmitting about 8% of the light. The crystal is wrapped in a spiral xenon flash lamp. The same lamps were used in photographic flashes. Maimon turns on the power. The lamp flashes. Intense white light bathes the ruby. The green component of this light is absorbed by chromium ions in the crystal. Remember, we said that in ruby, chromium absorbs green light. Electrons move to an excited state, then, through an intermediate long-lived level, begin to return to the ground state, emitting photons of red light. When there are enough photons, they begin to stimulate the emission of other photons by excited ions. The avalanche grows. Photons reflect between mirrors, passing through the crystal again and again, each time amplifying the avalanche. Some escape through a semi-transparent mirror. A pulse of red coherent light bursts out of the end of the ruby. The first laser pulse in history. N wrote down the result and sent the article to Physical Review Letters. The editors rejected the publication, deciding that the topic of lasers was already overloaded with speculative work. It was published in the British journal Nature. On August 6, 1960, the article, Stimulated Optical Radiation in Ruby, was published. It is one of the most cited physics papers of the 20th century. Maimon did not receive the 1964 Nobel Prize for the creation of lasers. This is still considered one of the most controversial decisions of the Nobel Committee in the history of physics. Ruby lasers are used today in medicine, including tattoo removal, treatment of age spots, and some ophthalmological procedures. The ruby laser pulse is absorbed by melanin, a dark pigment, much more strongly then by surrounding tissue. This allows for precise, localized action without damaging neighboring cells. The first laser pulse in human history was generated by quantum transitions of electrons in chromium atoms. This fact is rarely mentioned in popular materials about lasers, and in vain. Chromium is an antiferromagnet. What does this mean in practice? In iron, the atomic magnetic moments are aligned parallel. They all point in the same direction. The total magnetic moment is enormous, so a magnet attracts iron. In chromium, it's a different story. The atomic magnetic moments are aligned anti-parallel. One points up, the next down, and the next up again. They cancel each other out. The total magnetic moment is zero, so a regular magnet doesn't attract chromium. At a temperature of approximately 38 degrees Celsius, chromium transitions from an antiferromagnetic state to a paramagnetic one. This critical temperature is called the Néel point, named after the French physicist Louis Néel, who received the Nobel Prize in Physics in 1970 for his research on antiferromagnetism. Above this point, the thermal motion of atoms destroys the antiparallel ordering. Chromium becomes an ordinary, weakly magnetic metal. Why should we know this? Because the physics of antiferromagnets is not some academic curiosity. It is a fundamental phenomenon, the understanding of which is important for the development of next-generation magnetic storage devices. Research on chromium as a model antiferromagnet has directly contributed to our understanding of the physics underlying modern hard drives. On the Mohs scale of hardness, chromium is 8.5. For comparison, iron is about 4, copper about 3, and diamond is 10. Chromium is one of the 5 hardest metals. This is what makes chromium plating so effective. Even a thin layer of chromium on the surface of a soft metal dramatically increases abrasion resistance. Chromium's melting point is 1907 degrees Celsius, Fahrenheit, higher than that of iron and nickel. This is why chromium is added to steels and alloys for high-temperature applications. However, it also has a drawback. Pure chromium is brittle at room temperature. It does not deform plastically, it cracks upon impact. This is due to the specifics of its crystalline structure and its high sensitivity to impurities. Even trace amounts of nitrogen or oxygen dissolved in chromium dramatically increase its brittleness. This is why pure chromium is almost never used on its own, but only in alloys where other components compensate for its brittleness while preserving its key advantages, while preserving its resistance, hardness, grease resistance, and corrosion resistance. The route from chromite from the mine to stainless steel is indirect. Pure chromium is not needed to produce stainless steel. Ferrochrome is used instead, an iron-chromium alloy containing 50 to 70% chromium by weight. Ferrochrome is produced in electric arc furnaces. Chromite ore is mixed with a carbonaceous material, coke or anthracite, fluxes are added, and the mixture is melted at temperatures above 1500 degrees Celsius. The carbon removes oxygen from the chromium, reducing it to metal, the resulting molten ferrochrome, which, after solidification, is crushed and sent to steel mills, is an energy-intensive process. Producing 1 ton of ferrochrome requires 3 to 4 megawatt hours of electricity. This is why the largest ferrochrome plants are built in areas with low electricity costs: Kazakhstan, South Africa, and India. To obtain pure metallic chromium, which is needed in electronics, optics, and special alloys, other methods are used. First, chromium oxide is mixed with aluminum powder and ignited. The reaction is exothermic. The temperature in the reaction zone reaches several thousand degrees. Aluminum intensively binds oxygen, reducing metallic chromium. This is a thermite reaction, the same principle as in thermite welding mixtures. The second method is electrolysis. An electric current is passed through a solution containing chromium. Pure metallic chromium is deposited on the cathode. This same electrochemical process, but with controlled current and time, underlies galvanic chromium plating. The only difference is that chromium plating requires a thin decorative or protective layer, while metal production requires a thick deposit, which is then removed from the cathode. There is another significant history of chromium use, rarely discussed outside the professional community. Until the mid-10th century, Leather was tanned using plant-based tannins, tamshin secamins, extracted from oak, chestnut, and willow bark. The process was slow. The entire tanning cycle took from several months to a year. The resulting leather was dense and tough. In 1858, the first scientific results on the use of chromium salts in tanning were published. It turned out that trivalent chromium forms strong bonds with the protein chains of collagen, the main protein in leather. These bonds cross-link the protein chains, making the leather structure stable, resistant to moisture and decay. The advantages over vegetable tanning were striking. The process takes hours instead of months. The leather is soft, supple, and heat-resistant. Today, approximately 80 to 90% of all leather worldwide is tanned using the chrome method, from shoes to car interiors, from bags to car into leather coats. But this story has a dark side. Wastewater from tanneries contains significant amounts of chromium compounds. Under certain conditions, the trivalent chromium in the waste can oxidize to hexavalent chromium, the toxic form. This is why tanning is included in the list of industries with increased controls over the handling of chromium-containing waste. 2010, several orthopedic clinics in the UK almost simultaneously reported an inexplicable occurrence. Patients who had received hip replacements several years earlier are coming in, complaining of pain and weakness in their legs. X-rays show dark areas around the metal components of the prosthesis. Blood tests reveal elevated levels of cobalt and chromium ions. The metal prosthesis is dissolving inside the human body. Let's examine the mechanism. Metal-on-metal hip replacements are designed in which both the wide-shaped head and the acetabular cup are made of an alloy of cobalt, chromium, and molybdenum seemed like technological progress in the early 2000s. The previous generation of prostheses used a metal polyethylene pair, a metal head, and a cup made of ultra-high molecular weight polyethylene. The polyethylene wore out, the resulting microparticles caused inflammation, and over time loosened the prosthesis. A metal-on-metal pair seemed like a solution. The metal is harder, wears less. But reality turned out differently. With each step, the metal head slides in a metal cup. Microscopic alloy particles are torn off from the surfaces, and cobalt and chromium ions are released into the interstitial fluid. The metal particles trigger an immune system response, but not the usual one. Defense cells, attempting to absorb the metal particles, die and release inflammatory mediators. This leads to massive necrosis of the surrounding tissue. This phenomenon is known as metallosis. Some patients develop pseudotumors, accumulations of necrotic tissue, and inflammatory exudate around the prosthesis. Some patients lost significant muscle tissue in the thigh, and nerve damage was recorded. All of this occurred against a background of elevated levels of chromium and cobalt ions in the blood, which are toxic in themselves. The most problematic prosthesis was called ASR, articular surface replacement, manufactured by DePuy Orthopedics, a division of Johnson & Johnson. In August of this year, the company announced a global recall. Approximately 93,000 hip prostheses were recalled. Many patients underwent revision surgeries to replace the implants. These are complex, risky, and painful procedures. By 2013, approximately 10,000 lawsuits had been filed against Johnson & Johnson. In November 2013, the company announced it would pay approximately $2.5 billion to settle the first 4,000 cases. The total settlement ultimately exceeded the $1 billion. Today, metal-on-metal pairs are practically no longer used in hip prostheses. Ceramic on polyethylene and ceramic pairs have replaced them. They ensure minimal wear without the release of metal ions. Cobalt-chromium alloys have not disappeared from medicine. Dental crowns and bridges, spinal structures and instruments are all still made from such alloys. But designs in which such an alloy operates in a friction pair inside a joint are deemed unacceptable. Chromium doesn't just lie in ores and pollute factory runoff. It participates in the global biogeochemical cycle, the constant circulation of matter between the lithos, hydrosphere, atmosphere, and biosphere. It all begins with weathering. Ultramafic rocks, rich in chromite, are exposed to the surface and undergo chemical and physical weathering. The chromite gradually oxidizes. Trivalent chromium is released and partially enters solution, although with great difficulty because it is poorly soluble. A small portion is oxidized to the hexavalent form by manganese oxides, which are present in the soil and act as natural oxidizers. Hexavalent chromium is highly soluble and begins to migrate with soil water. It ends up in rivers, groundwater, and ultimately the ocean. The concentration of chromium in seawater is low, about 0.2 milligrams per liter, but it is constantly present. In the ocean, chromium is absorbed on the surface of settling organic particles, plankton remains, and detritus. Along with them, it slowly sinks to the bottom. There, it settles as part of marine sediment. Layer after layer accumulates in sedimentary rocks, year after year, millennium after millennium. And here's the most important thing. Plants are also involved in this cycle. Some are capable of accumulating chromium in significant concentrations, tens and hundreds of times higher than ordinary plants in the same soils. Such species are called hyperaccumulators. This property is currently being actively studied in relation to phytoremediation, the cleanup of contaminated soils using plants. The idea is simple. Plant hyperaccumulators in a contaminated area. Wait for them to accumulate the metal and then mow and dispose of the biomass along with the chromium. Sedimentary rocks are the planet's archive. Each layer records the conditions that existed at the time of its formation: water temperature, atmospheric composition, ocean chemistry. Chromium is a special witness in this archive because its behavior is critically dependent on one factor: the presence of free oxygen in the atmosphere. Let's explain it simply. Trivalent chromium is an insoluble form found in minerals. It oxidizes to hexavalent chromium only in the presence of a strong oxidizing agent. In natural conditions, this oxidizing agent is molecular oxygen. No oxygen, no oxidation, no soluble chromium, no release into the ocean or sediments. Now, about isotopes. Chromium has several types of atoms, each differing in mass. These are called isotopes. When trivalent chromium is oxidized to hexavalent chromium, these types are easily separated. Heavier atoms are slightly more readily soluble and enter the ocean. By measuring the ratio of heavy to light chromium isotopes in ancient marine sedimentary rocks and comparing them to a standard, we can determine whether free oxygen was present in the atmosphere at that time. It is this method, chromium isotope geochemistry, that has made it possible to independently confirm and refine the timing of the Great Oxidation Event. The Great Oxidation Event is the moment in Earth's history when the concentration of free oxygen in the atmosphere first rose to levels that can be recorded in the geological record. This occurred approximately 2.4 billion years ago during a period geologists call the early Proterozoic. Cyanobacteria were the culprits. These microorganisms mastered photosynthesis, releasing oxygen as a byproduct. Accumulating in the atmosphere, oxygen irreversibly changed the planet. For most of the anaerobic bacteria and archaea that had previously inhabited the Earth, this was a true catastrophe. Oxygen is toxic to anaerobic life forms, oxidizing their enzymes and destroying cellular structures. Most anaerobic organisms died out or took refuge in anaerobic pockets, deep in the soil, in bottom sediments, and in the guts of other creatures. Those that survived and adapted gave rise to all the diversity of aerobic life, including us. Robert Frey of the University of Copenhagen and his colleagues published key papers on chromium isotope geochemistry in leading scientific journals. In their data on samples from South Africa, Canada, and Australia confirmed that the chromium isotope signal in marine sediments changed sharply around 2.4 billion years ago, precisely where other geochemical tracers record the onset of atmospheric oxygenation. The small gray metal in your kitchen faucet also bears a record in sedimentary rocks of the moment when our planet became habitable as we know it, or moist we know it. There is another aspect of chromium in the biosphere that is rarely covered in popular literature. In the 1980s, microbiologists discovered that some bacteria can use hexavalent chromium as an electron acceptor during respiration, much like we use oxygen. For these bacteria, chromium is not poison, but food. We're talking about several groups. Pseudomonas are widespread soil bacteria. Bacillus are spore bacteria resistant to extreme conditions. Desulfovibrio are bacteria that thrive in oxygen-free conditions. These microorganisms convert hexavalent chromium to trivalent chromium using organic compounds as an energy source. The result, soluble and hazardous hexavalent chromium is converted into insoluble and harmless trivalent chromium, which precipitates and stops migrating in water. This discovery has direct practical implications: the biological remediation of contaminated sites. Instead of excavating and removing tons of contaminated soil or injecting chemicals, conditions can be created for the growth of chromium-reducing bacteria right on site that will slowly but reliably convert hazardous chromium into a harmless form. In practice, is more difficult than it sounds. It's necessary to maintain the correct acidity and temperature and provide the bacteria with nutrients. Nevertheless, field tests at contaminated sites, including in the United States, where thousands of sites with hexavalent chromium contamination exist, have demonstrated the true effectiveness of this approach. Once again, nature has found a solution before us. The final question, and perhaps the most profound, is this: why does life use so little chromium? Iron is in the hemoglobin of each of us. Zinc is in hundreds of enzymes. Copper is in key proteins of cellular respiration, without which the very existence of cells is impossible. Without oxygen. Magnesium is in every chlorophyll molecule, while chromium is only a trace element in negligible concentrations. Why? The answer lies in chronology. Life on Earth arose approximately 3.8 to 4 billion years ago in a reducing atmosphere, almost devoid of free oxygen. Under such conditions, chromium existed exclusively in the trivalent form, poorly soluble, practically insoluble in water. The first organisms built their biochemistry from what was dissolved in the primordial ocean. Iron existed in a reducing atmosphere in a form that was highly soluble in water, meaning it was readily available. It became the basis of biochemistry. Hemoglobin, respiratory chain proteins, and iron-sulfur proteins were also available. Copper, manganese, nickel, and vanadium were also available in the necessary forms. Chromium was not. It remained locked away in insoluble minerals and practically never entered the primordial ocean. When oxygen appeared 2.4 billion years ago and trivalent chromium began to oxidize to a soluble hexavalent form, the biochemistry of life was already established. Evolution had already invented the basic metalloenzymes over the previous billion years. Integrating a new metal into an already functioning biochemical machine was a task for which evolution lacked the opportunity, time, and selection pressure. Chromium remained on the periphery, important but not central. And yet life found a place for it. That very same glucose tolerance factor, discovered by Schwartz and Moritz. That cornerstone of biochemistry that regulates insulin sensitivity. In an era when type 2 diabetes and insulin resistance have become among the leading global health problems, this evolution, morally marginal element is suddenly becoming relevant. Chromium is a chameleon of metals. It exhibits different colors, different properties, and a different character under different conditions. Its atoms have recorded the history of oxygen on Earth in sedimentary rocks. Its compounds color rubies red and emeralds green, using the same ion in different crystal environments. Dukkha. Its 3 nanometer thick film protects stainless steel, a material essential to modern medicine, aviation, and the food industry. The first laser pulse in human history erupted from a ruby crystal thanks to the quantum transitions of its ions. They also poisoned the groundwater in Hinkle, darkened Van Gogh's sunflowers, destroyed the tissue around thousands of hip prostheses, and became a tool of geopolitical struggle into world wars and the Cold War. One element with 24 protons in its nucleus. Science isn't a list of properties and applications. It's a story about how matter interacts with the world, how the same atom can save life in a surgical instrument and destroy it in polluted water. How a tiny difference in the distance between atoms, less than an angstrom, changes the color of a precious stone from red to green. How a metal that life has barely used for billions of years turns out to be needed right now. The 24th element on the periodic table, chromium.